Hello, my name is Ki-Joune. I'm working at Busan National University and I explain OGC IndoorGML, which is a standard for indoor spatial information. First of all, I'd like just briefly introduce OGC, which stands for Open Geospatial Consortium. It is a standard development institute. They produced quite a big number of the standards like IndoorGML and KML and CTGML, GML and so on. So before explaining IndoorGML, I'd like to explain some other standards which also deal with indoor space, like IFC, Industrial Foundation Class, or CTGML. IFC is a standard made by Building Smart. They focus on construction of a building. And CTGML, it is a OGC standard, and it is for modeling the three-dimensional cities. Comparing with IndoorGML, with the previous ones, while given indoor space like this one, while IFC and CTGML, they focus on how to describe the object modeling. For example, they are concerned on how to represent the surface object, or the door object, or some other furniture object, and so on. But IndoorGML, we try to give the modeling for the space in indoor. Like, for example, this room space, or in this case, this is a door space. So we look at how to model indoor space in terms of the space. So we are modeling the space in indoor, not the object like this one. This is the main difference between the previous standard dealing with indoor space and IndoorGML. This is the main motivation of IndoorGML. So we focus on the space modeling of indoor space. Okay, so the first concept of IndoorGML is the space cellular model. So we define a given indoor space as a set of non-overlapping cells. For example, if you are given this room, this building, then we consider that it is a set of several rooms, corridor, and the stairs, and the restroom, and so on. So we look at an indoor space as a set of cells. So this is the main concept, and we call it cellular space model. So cellular space model is defined as a set of cells where the cells are non-overlapping, and the union of all cells is a subset of any given indoor space, which is either two-dimensional or three-dimensional. And it is better to have each cell as a unique identifier. So this is the main concept. So, in order to explain IndoorGML, we have to look at the several different aspects of cells. For example, geometry of a cell, and topology between cells, and the multi-layered space model, and the semantics of cells, the cell partitioning, the hierarchical structure, and so on. So I will explain it one by one. So first of all, the geometry. We describe the geometry of each cell with three different options. The first option is we don't define the geometry of cell. Instead, we include a reference to an object of other data set. For example, in this case, we have a CTGML data set, and we include an identifier, which is a pointer to the object defined in other data set. This is the first option. The second option is we include all the geometry. So either three-dimensional geometry as a solid or the two-dimensional object of surface. So if we consider indoor space as a multi-level two-dimensional data, then it can be a two-dimensional object. Or if we define indoor space with three-dimensional space, the geometry of each cell should be defined as a three-dimensional object like a solid. This is the second option. And the third option is we don't include anything. So in this case, we only include the topology between cells, the relationship between cells, but we don't include any geometry. So these are the options to describe the geometry in IndoorGML. But in this case, these three options are not exclusive. For example, we may take option 1 and option 2. That means we include the reference to another object in the external data set using option 1, for example, with the GML identifier, and we can also include the geometry in IndoorGML itself. So it is any combination of this option would be possible as well. This is the geometry. And the second one is a topology between two cells to explain the relationship between two cells. This is one of the key concepts of IndoorGML. We have a theoretical background from a point correct duality, which explains the conversion process from the original space, that means the topographic space, to the dual space, which is a network or graph space. For example, if we have so we suppose that we are in a three-dimensional space and we have a three-dimensional object, then it can be mapped to n minus k dimensional object, where n is the dimensionality of space and k is the dimension of a given object. So solid is a three-dimensional space in three-dimensional solid is a three-dimensional object in three-dimensional space. So n is 3 and k is 3. So it is mapped to zero-dimensional object in dual space or the graph space. So it is a node. And the surface or boundary shared by two rooms or cell, since it is a two-dimensional object in three-dimensional space, so n is 3 and k is 2. So it is mapped to one-dimensional object, which is a line. The solid cell is mapped to a node, and the boundary shared by two cells, it is mapped to one-dimensional object, that is an edge. So with the node and edge, we can construct a graph or network to explain the topological relationship between cells. This is the key idea. So with this idea, we can describe the topological relationship of indoor space. For example, if you are given an indoor space like that, R1 is a room and R2 is another room, and D1 is it is not a room but it is a cell explaining a door space. In this case, we consider a door as a small cell, and wall is also in this case considered as a cell. So from this topographic space or primal space, we can derive a dual space where each cell is mapped to a node. R1 is mapped to node R1 and D1 is mapped to node D1, and even the W6, the wall space, is also mapped to a node W6. And the edge in this graph, it explains the adjacency relationship. For example, R1 is adjacent with the cell D1. So we have an edge connecting R1 and D1 and so on. So for this space, we can construct a graph. So we call it adjacency graph because the edges of this graph explain the adjacency topological relationship. So this is the main idea. And if we only interested in the connectivity means the relationship between two cells where we can pass through. For example, we can go from R1 to D1. So this edge is a connect. So it explains the relationship between D1 and R1 as connectivity. So if we are only interested in the connectivity, then we can remove all other edges which are non-navigable. Then we can only have a node and the edges of connectivity. So this is called the connectivity graph. So from adjacency graph, if you want, we can derive a connectivity graph. This is another interpretation of the space duality between the original space and graph space. But in this case, we consider wall as a kind of a paper wall. We don't accept the spatial extent of wall. In this case, wall is considered as a simple boundary shared by two rooms. So we have a little bit simplified graph where the D1 and D3, it explains the connectivity between room R1 and R2, and B3 and B2, these are only the adjacent but non-navigable. So if we remove the dotted line, we can obtain the connectivity graph. So this is another interpretation, but the main idea is with using the point-credit duality, we can derive the network space or graph space from the original space. This is a topographic aspect of cellular space model. The next one is called multi-layered space model. It is also a very important concept in IndoorGML. Suppose that you are given indoor space like that, but we have two different interpretations. The first one is, if you look at we may find a stair in the center of this room. So for a person on wheelchair, we cannot pass through this stair. So it should be divided into two small cells. So depending on the situation, if you are on a wheelchair, you have 1, 2, 3, 4 rooms. And if you are not on wheelchair, we have only 3 rooms. So we have two different interpretations of primal space, and we have two different dual space, the network graph. So we have, in this case, we have only 3 nodes for rooms and 1 external space. So in this case, we have 1, 2, 3, 4 nodes and 1 for external space. So we have two different interpretations. For each interpretation, we can describe it as a single space layer. So this is one space layer, and this is another space layer. So we have two different space layers. That means we have a multi-space layer. And in addition to different layer, we may connect the several space layers using interlayer connection. For example, this room is divided into 2 rooms. So we have interlayer connection with this room and these 2 rooms. So we have an edge called interlayer connection between R1 and R3A and R3B. This is a multi-layered space model. Normally in indoor space, even though there is one single indoor space, it can be interpreted in different ways. So the concept of multi-layer space model is very useful for many applications. All right, the next aspect of the cellular space model is the semantics of each cell. Each cell can be classified into several categories like room, door, corridor, or stair, or restroom, or meeting room, and so on. And we have a quite nice classification of indoor space, OmniClass, which is also a standard. So IndoorGML take the classification given by IndoorGML, OmniClass. In OmniClass, they give the classification in terms of a function, in terms of a form. For example, in terms of functions, they have the classification like a kitchen, elevator shaft, and office space, and so on. So we take this classification. And in addition to the classification, we also define some attribute to each cell and the cell boundary. For example, we can define the name of cell, the usage of cell, function, and so on. And for example, the boundary, if it is a door, we may define the direction. So there is some door where we can enter from one direction, but it is not allowed to go back from the other direction. So we can define the direction to the surface, and we can also define the accessibility. For example, some door is accessible during the daytime, but the nighttime it is not accessible. So we can define such kind of attributes to each cell or the cell boundary. And this is an example of the semantics defined for indoor navigation model. Indoor navigation model is a application module of IndoorGML. So here we defined the anchor space and general space and connection space, but for the detailed definition, I'd like to recommend you to read the document of IndoorGML. Here, but I'd like to mention one very interesting classification, which is called anchor node, which is to connect indoor space and outdoor space. Normally, anchor is defined as a gate. The gate is defined as an anchor. For example, if you have a big building and if you have there are two gates, then each gate can be defined as an anchor. So anchor, it plays a very important role for several things. The first, it connects the indoor space with outdoor space. For example, here we have a connectivity graph, and it connects with the graph of ground transportation network, for example. So this is the one very important role of anchor node. And another role is to anchor node, we can define some additional attributes. For example, if you want to define a transformation of indoor space, which is defined as a relative coordinate reference system, to outdoor space, where outdoor space is defined as an absolute reference system, then we can define the transformation parameters as an attribute of anchor node. This is one possible application of anchor node. And for example, if necessary, we can define the further information of this indoor space as an attribute of anchor node. This is another application. So there are many very interesting applications of anchor node. And the next very interesting and important concept of IndoorGML is space partition. This is a very good example which explains why we need a space partition. Suppose that we are given this indoor space where this long corridor is defined as one single indoor space. Then suppose we have a fire. That means this node is blocked by this file. It means we don't have any evacuation path from this point to, for example, the staircase, because this node is blocked. But if we divide this corridor into small pieces, then there is a fire. Then even though there is a fire, this node can be blocked, and we may have still the evacuation path. So this explains the reality much better than the previous one. We need, for many cases, the space partitioning. For example, if you are given a subway station, which is in fact one single cell, but with one single cell, we cannot implement a very interesting and useful application. In this case, we have to divide the cell of subway station into several small cells by using different attributes and the geometry and so on. In this case, we need the space partitioning. There are many different cases where the space partitioning is very critical. For spatial partitioning, each spatial partitioning can be represented as one single layer. For example, here, N6 is one single node where it is divided into two small cells, N61 and N62, in order to another partitioning. Then, for each partitioning, we can construct one single layer and make a correspondence between the partitioned cell by using interlayer connection. And the hierarchical structure is also very useful concept in indoor space. For example, if you are given a shopping mall is divided into east ring and west ring. So there is a hierarchical structure, and each ring is divided into several floors and so on. So there is a hierarchical structure of a given shopping mall. So this hierarchical structure is very useful to explain the indoor space. We can very easily construct the hierarchical structure by using multi-layered space model. For example, if you are given a very detailed the partitioning of indoor space, then we have one single space layer, and then if R1 and R2 are merged into one single node N1, then we can make another space layer and so on. So between the layer we can make an interlayer connection. So finally, at the top we have one single node which includes all the entire indoor space. And this is a root node, and from the root node we can make a hierarchical structure using a multi-layered space model. This is one very interesting application of a multi-layered space model. Alright, the final concept is called it is for external reference. So I explained the external, how to use external reference during the geometric representation of a cell. But it is very useful to integrate IndoorGML with other data set. This is a good example how to integrate the data. So suppose that you are given a CityGML data. So this is a CityGML data for one given building. So this is one room. So with the GML ID, the identifier is given like that. And this is an IndoorGML document. So within IndoorGML document, we include the external reference here. So with the information system and the identifier of the object. So information system can be, for in this case, the name of the file, and the object identifier, the external object is identifier of the object in CityGML. This can be a good example how to integrate with the IndoorGML with other data sets. But it could be not only the file name and object identifier, it could be a database, the URL of the database, and the SQL statement. So it could be, it is very flexible. So we can make the integration of IndoorGML with other data set, whether it is in file system or it is in database, using the mechanism of external reference. Okay, this is a very brief explanation of IndoorGML. In summary, IndoorGML is approved in 2014 and published in 2015 by OGC. And key concept of IndoorGML, it is first, it is complementary to other standards such as CityGML, IFC, or KML, etc. So it is very strongly recommended to integrate IndoorGML with other data sets. Of course, it is possible to define a standalone IndoorGML, but it is much better to integrate it with other data sets. And the key idea of IndoorGML is a cellular space model, where we represent Indoor space as a combination of the set of volumetric cells. And it is very strong in describing topology. Okay, this is the very brief introduction of IndoorGML. Thank you.